In this video, we will analyze the conditions that a vestigial sideband filter must satisfy. In this picture, we have an example of the frequency response of a modulating signal with a given bandwidth W radians per second, and here we have the frequency response of a double sideband modulated signal with double amplitude. We can see here the two sidebands of this modulated signal. In a single sideband modulation, we have ideal filters to remove one of the sidebands. For instance, with this filter, we can remove the lower sideband, and with this filter, we can remove the upper sideband. Theoretically, everything works perfect. However, these filters are ideal filters. They have an instantaneous transition from 0 to 1 or from 1 to 0 around the carrier frequency omega c, and it is not possible to implement filters with this instantaneous transition from 0 to 1 or from 1 to 0. In a vestigial sideband modulation, these ideal filters will be replaced by implementable filters, filters with a smooth transition about omega c from 0 to 1 or from 1 to 0 around this carrier frequency. Therefore, in the transmission generation scheme based on direct filtering, just ideal filters will be replaced by implementable filters. And now we are going to analyze the conditions that these implementable filters must satisfy to work appropriately. To do this, first we will obtain the analytical expression of the modulated signal here at the output of the transmitter. Basically, what we have is the convolution of the double sideband modulation with double amplitude, the modulating signal times a carrier with double amplitude, and the convolution is with the impulse response of this vestigial sideband filter. In the frequency domain, convolutions becomes products, and we have the product of the frequency response of the double sideband with double amplitude, shifted versions of the frequency response of the modulating signal shifted to omega c and to minus omega c, and then the product with the frequency response of this vestigial sideband filter. Now this signal is transmitted, and we will assume that at the receiver we receive exactly the same signal without distortion, and we will use a coherent receiver to try to recover the modulating signal. Here we have the analytical expression in the frequency domain of the received signal. First, we have a product with the cosine to obtain x of t, and a product with a cosine in the time domain becomes the addition of two replicas of the spectrum of the received signal, is one with half of the amplitude, and one of them is shifted to omega c and the other one is shifted to minus omega c. Now, by replacing the expression of the frequency response of the received signal in these two replicas here, it is straightforward to arrive to the expression for the signal that we have after the product with the cosine. Finally, the low-pass filter will remove the components that are located in frequencies around 2 times the carrier frequency and minus 2 times the carrier frequency. These are these two terms that we have here. This will be eliminated after filtering, and here we have the final expression of the frequency response of the output of this receiver, just proportional to the spectrum of the modulating signal, which is what we want to recover, and then we have the addition here of two shifted replicas of the frequency response of the vestigial sideband filter. If now we analyze this expression, we can see that the equivalent effect is to have a filter that is filtering the modulating signal and that has this equivalent response. The addition of these two replicas of the frequency response of the vestigial sideband filter. One is shifted omega c, the other one is shifted minus omega c. This means that this equivalent filter must have an ideal response in the bandwidth of the modulating signal. It is necessary to have a constant modulus and a linear phase. This means that the addition of these two replicas must have a constant modulus in the bandwidth of the modulating signal. In the initial frequency response of the filters, this means that an odd symmetry around omega c must be necessary in the interval between omega c minus the vestige and omega c plus the vestige, in the interval where we have the transition from 0 to 1 or from 1 to 0. And delta W is the bandwidth excess or the vestige expressed in radians per second. Here we have a couple of examples of filters satisfying these conditions for the upper sideband option and for the lower sideband option. It is interesting to remark that the response out of the frequency band of the double sideband modulation is meaningless because there are no frequency components of the double sideband signal out of this range. Now the addition of the two shifted replicas corresponds to this shape shifted here minus omega c and this shape shifted here plus omega c. This for the upper sideband example. Or equivalently, this is shifted here minus omega c and this is shifted here plus omega c for the lower sideband variant. In any case, to have an ideal response here with the addition of these two replicas is equivalent to have an odd symmetry here or here around omega c for these filters. With respect to the bandwidth, now the bandwidth of the modulating signal will be incremented by the size of the vestige of these filters. And therefore, the bandwidth of a vestigial sideband modulation is equal to the bandwidth of the modulating signal plus the bandwidth of the vestige in radians per second or in hertz.